This is your review for your Unit 7 test. First question asks us to consider this enthalpy diagram and label the following. So first, let's start with reactants and products. Reactants are what you begin with, so that should go at the beginning. And products are what you produce, what you end up with, so that goes at the end. This axis is the reaction pathway. You can think of it as time. It's how far along we are in the progress of the reaction. The other things that we need to fill in are all related to energy. So first, let's start with the net energy change during the reaction. So my reactants are at 150 and my products are at 50. So the difference between these two is going to be my energy change. You know this as delta H. Activation energy is how much energy the reactants need to absorb to get to the top of this hill. So reactants to the top of the hill, this line represents activation energy. We abbreviate that as EA. Energy absorbed by reactions and energy released by products. So every reaction has an endothermic portion where energy is absorbed in order to break the bonds of the reactants, and an exothermic portion where energy is released as we form bonds. So the energy absorbed by the reactants, that's going to be the same as EA. It's the energy absorbed in order to get to the top of this hill. So it's the same thing as EA, and it's represented by this line. The energy released is going to be the top of the hill down to where the products are, which is represented by this line. Next question asks us to find delta H for this reaction. So since you have an enthalpy diagram and the axis is labeled, we can actually get the real number for delta H. So we labeled delta H as the difference between reactants and products. Reactants are at 150 and products are at 50. So to find delta H, we're just going to do the products and reactants, the difference between the two of them. So if we do that, we see that the difference is going to be 100 kilojoules. The next question for us to think about is this a positive 100 kilojoules or a negative 100 kilojoules? So we start with reactants, and then we have to lose energy in order to become products. So my delta H is going to be a negative number. The reactants start higher than the products. So in order for this to happen, the reactants must lose energy to become products. So I know that delta H has to be a negative number because I have to lose that energy in order to become a product. Next question, make a claim about whether this is endothermic or exothermic. So this reaction is exothermic. Ways that we know that delta H is negative. And because reactants are higher energy than the products. So again, a reaction has two parts. There's an endothermic part and an exothermic part. In this case, the energy released by bond formation is bigger than the energy absorbed by bond breaking. So overall, our reaction is exothermic. Last question on this page asks us to compare the stabilities of the reactants and the products. So what you need to remember is that higher energy means less stable. So in this case, because products are lower, they are more stable. Let's go ahead and look at the next page. So on the next page, we are given a reaction, and we are given the heat that has to be absorbed in order for this reaction to occur. So first question asks us, what is the delta H of this reaction? So in this case, delta H is given to us. It is 67.8 kilojoules. Now we got to ask ourselves, is this going to be a positive 67.8 or a negative 67.8? So the energy is a reactant, which means that in order for this reaction to occur, energy must be absorbed. So in this case, it's going to be a positive 67 kilojoules. Energy is absorbed, which means endothermic. So delta H is going to be a positive number. Next question says, well, what is the change in heat? How much heat is going to be released if I form 1 mole of nitrogen dioxide? So if we look at the balanced equation, if I make 2 moles of nitrogen dioxide, I would release this amount of energy. So the question is saying, well, what if I only made 1 mole? So we know that if we have 2 moles of NO2 formed, it's this much. So we can do dimensional analysis. So I want to know if 1 mole of O2 is formed, NO2 is formed, how much energy is going to be absorbed. So I know that for 2 moles of NO2, that I produce a positive 67.8 kilojoules. So mole will cancel mole. So the only thing left is going to be kilojoules. So in order to solve this, I just have to have this number. So 67.8 divided by 2 is going to give me 33.9 kilojoules. And that's going to be a positive 33.9 because it's endothermic. Energy must be absorbed. Is the reaction endothermic or exothermic? We know that it's endothermic because delta H is positive and energy is a reactant, which is the same thing as saying that energy is absorbed. Okay, next question says, if a quarter of a mole of nitrogen reacts, how much heat is absorbed? So we know that if I've got one mole of N2 from the balanced equation, I'm going to need to absorb a positive 67.8 kilojoules. So once again, mole cancels mole. So if I only react a quarter of a mole of nitrogen, I'm going to make 16.95 kilojoules of energy. So the next question is almost the same as the question before it, except this time we're going to take it one step further, and we're going to calculate grams of N2 instead of just moles of N2. So for this one, I'm going to start with 156 kilojoules of energy, and that is how many kilojoules I produce for each mole of N2. So 67, a positive 67.8 kilojoules are absorbed for each mole of N2. So if I solved right here, my answer would be how many moles of N2. But I don't want moles, the problem asks for grams. So 1 mole of N2 is going to have a molar mass of 28 grams. So whenever we solve this, we end up with 64.42 grams of nitrogen. Next question asks about entropy. So entropy is kind of a weird word that describes the state of a system. It can describe the amount of disorder, the chaos of the system. So for each of the following, determine if disorder of the system is increasing or decreasing. So if we think about it, if we take ice, which is a solid, a nice, neat, orderly solid, and we melt it, it's going to change into this liquid, which is sort of disordered. The particles are all sliding about past each other. So in this case, we go from a very neat, orderly system to a more chaotic system. So we would say that disorder, that entropy is increasing. Methane crystallizes into a solid. So in this case, we're going from a gas to a solid. So we're going from a gas where particles are flying around all over the place to a nice, neat solid. So in this case, the disorder or entropy is decreasing. Iodide sublimates into a gas. So we're going from solid to gas. This is the exact opposite of the one that we just saw. So I'm going from a nice, neat solid to a chaotic gas. So we would say that entropy is increasing. Water condenses on a cold can. So if we are condensing, that means that we are going from gas to liquid. So this is pretty much the opposite of the first one. In this case, entropy would be decreasing. We're going from a chaotic, fast-moving gas to a slower, more orderly liquid. Let's go to the next page. Provide an example of a phase change that is endothermic and one that is exothermic. So endothermic would be any phase change where we are absorbing heat. So you could use solid ice turning into liquid water. In order for an ice cube to melt, the ice cube has to absorb energy. So that would be endothermic. Exothermic is any time where we are losing energy or getting rid of energy. So if we were to use the same example, that would be the opposite. That would be going from liquid water to solid ice. So in this case, we're starting with water, and the water's got to cool down. It's got to lose energy in order to become solid ice. So that would be exothermic. The next question asks us to consider the graph and asks about what is happening during the plateaus. So what is happening during the flat parts to the potential energy and kinetic energy. So let's focus on this plateau right here. So during the flat parts, this is where we're having a phase change. So in this case, because this is a heating curve, this would be going from a solid to a liquid. Notice that temperature is staying constant. So my temperature is not increasing, it's staying constant. So we would say that the potential energy during this part is being used to convert the solid into a liquid. So potential energy is increasing. The kinetic energy is the energy of motion. This is going to be staying constant. And we know that because temperature is constant. So the potential energy of the particles is increasing, but the kinetic energy is constant. That's because the energy that would normally go towards heating, that energy is being stored as potential energy to cause the phase change. Last question asks us to consider the reaction illustrated here and determine which bonds are being broken or formed, if it is endothermic or exothermic, and then to draw a potential energy diagram. So first, let's look at the bonds that are broken. If I look here, I've got an end-to-end triple bond. I don't see any of those over here, so I must break this bond in order to form this product. I also don't see any O to O double bonds, so I know that that bond is being broken as well. Which means, since all these bonds are being broken, The bonds that are being formed are going to be a nitrogen to oxygen single bond and a nitrogen to oxygen double bond. Next question asks us to use this information in order to determine if the reaction is going to be overall endothermic or exothermic. So this is where we'll need to look at our bond enthalpy sheet. So this sheet has all of the bond enthalpies, and it lets you know if they're single or double bonds and what's going on. So we're going to refer to this. So as far as the bonds that are being broken, breaking bonds requires us to absorb heat, so that's endothermic, and forming bonds requires us to release heat, which is exothermic. So as far as bonds being broken, I have one nitrogen to nitrogen triple bond and one oxygen to oxygen double bond. So if we look, the nitrogen to nitrogen triple bond is going to have to absorb 941 kilojoules to be broken. The oxygen to oxygen double bond is going to need to absorb 495 kilojoules of energy. So I'm going to take these two numbers and add them up. So whenever I do 941 plus 495, I end up with 1,436 kilojoules. Because this is endothermic, this number will be positive. Now I'm going to do the same procedure. This time I'm going to look at the bonds that are being formed. So I'm going to form one oxygen to nitrogen single bond and one oxygen to nitrogen double bond. So my oxygen to nitrogen single bond, in order to form that bond, I have to absorb 201 kilojoules. And to form a nitrogen to oxygen double bond, I need to release 607 kilojoules. So once again, I'm going to add these up, and I get 808 kilojoules. This is exothermic, so this number is negative. Now what I need to do is take these two numbers, put them together, and determine whether this reaction is overall endothermic or exothermic. Remember, a reaction has an endothermic part where energy must be absorbed to break bonds, and an exothermic part where we must release energy in order to form bonds. So whenever we add these two numbers together, we see that the endothermic part is going to be bigger than the exothermic part. So whenever I add these together, I know I'm going to get a positive number. I get positive 628 kilojoules. So because this number is positive, overall, this reaction is endothermic. Okay, next question asks us to draw the potential energy diagram. So our potential energy diagram, the y-axis is potential energy. And the x-axis is going to be our reaction progress. So because I found my delta H to be a positive number, I know that in order for this reaction to occur, I have to absorb energy. So that means that my reactants must start down here, so nitrogen and oxygen. And in order for this to work, I'm going to have to absorb energy. So this is my delta H. And these are my products, so NO2. So then you just connect these lines with the big hump like that. And the difference between them is my delta H.